balance torques problem. Want to know which of these is the most difficult to the least difficult. Basically, we're asking here, which of these hands will have to provide the most torque, and which has to provide the least torque, from the most to the least torque for these 4 scenarios. Question? 20 more seconds. I'll stop at 145. 145. Okay, very good. He is right. You can just sort of make up some units here, kind of like we did in lab. This is like with the meter stick and the mass is hanging off. This has a torque. If this is 1 meter, it has a torque of 1,000 grams times 1 meter. So I'll just say it's 1,000. These aren't real torque units, by the way. I'm just sort of throwing out numbers. Here I have 500 times 1 plus 500 times 1/2, which is 250. So this has 750 is our torque. Over here I have 1,000 times 1/2, so that's 500. And here I have 500 times 1, or 500. So those are just sort of rough measurements of the torque. But again, not the right units, right? Because I'm going to convert SI, I have to multiply times G. But this clearly has the most torque at 1,000, then 750, and then these two are the same. This one has a bigger mass, but it's a shorter moment arm, so it has the same torque as the 500 grams at 1 meter. What's just in there? All right. So B is the right answer. 2 buckets spinning in a horizontal circle. It starts to rain. What happens to the buckets as they fill up with water? Okay, I'll stop at 130. 130. Okay, let's see. Y'all are pretty much evenly split. The buckets slow down because angular momentum is conserved, or the buckets continue to rotate at constant angular velocity. All right, let's try it again. I'm going to just open it back up. It is either A or B. You can ask your neighbor what they put and see if you can convince one another otherwise. Right. So turn to your neighbor, ask them what they put. It is either A or B. All right. Let's shoot for about a minute here. 1 minute, 10 more seconds. A lot better this time. 1 minute. Okay, A is the right answer. We had a very similar question to this. Remember on chapter 5, I think, when we did momentum, the cart that was traveling along in a straight line and it filled up with water, and it slowed down for a similar reason, except linear momentum was conserved instead of angular momentum. So here, angular momentum, L, is equal to I omega, and this is always going to remain constant as long as there are no outside forces or outside torques that are being exerted on the system. And when I add water to the buckets, my moment of inertia increases, so that means my angular speed has to decrease. So A then is the right answer. I goes up, so omega has to go down. You remember that question we had in chapter 5 before, the train car going up for water? All right, moment of inertia is which of these? Stop at 50 seconds. 50. All right. It is the rotational equivalent of mass. Remember when we're talking about linear motion, we deal with mass. It is, except now we're talking about in a rotational system. So we call that the moment of inertia. The point at which all forces appear to act. No. And then, wait, who put the time at which inertia occurs? The moment of inertia? Who was that? It's the rotational equivalent of mass. Okay, I is mr squared. That's our moment of inertia. Okay, and a rigid body is an equilibrium. We sort of mentioned this briefly, and we're going to do this in the next section. If which of these is true? Remember, guys, equilibrium means not only is alpha equal to 0, but for an object to be in equilibrium, it also has to be the case that it can't be accelerating. I can have an object moving along in a line, and I can have an object rotating, and for it to be in equilibrium, both of those have to be equal to 0. That the angular acceleration and the linear acceleration have to be equal to 0 for it to be in equilibrium. All right, just a few more seconds. 125. very good. Okay, now I want to rank these in order of largest to smallest, the 5 torques that are provided by these forces, which is the larger torque and which is the smallest torque, and then those in between. You're not aware of this 45, sine of 45 is root 2 over 2, which is about 0.7 or so.
That black dot is where it's rotating.
Right, it's rotating at the black dot. Pretty well. About 10 more seconds. 145. Okay, excellent. A is right. We want to first find the largest torque, and you can sort of go through like we did before and just write down the torques. If you assume this bar is 1 meter, then I have 2 Newton meters here. That's 2 newtons times 1 meter. Here I have 2 times a half a meter, which is 1 Newton meter. Here, what is my torque for C? It's 0, right? So here my torque is 0 because this angle is 180 degrees, and the sine of 180 is 0. Remember, torque is RF sine theta, so that doesn't provide any torque at all. Here my torque is 2 Newton meters, and then here it's going to be 4 newtons times 1 meter times sine of 45, which is more than 2, bigger than 2. The sine of 45 is bigger than a half. All right, so that gives us this one is the biggest. These two are equal. This one is next, and then this one is the smallest, which is A. All right, is that right? Yeah, A is the right answer. All right. I would expect to see some of these ranking type problems, either by moments of inertia or torques, in the multiple choice part of the exam. All right, that's it. So for the exam, get a window here. We're going to have chapters 7 and 8. So chapter 7 was largely kinematics. I would expect to see some kinematics problems. We worked several in class, and you'd have some in your homework where using those kinematics equations, finding the angular velocity, angular acceleration. You also need to remember how to translate the linear quantities to the tangential or to the angular quantities. And then that's really all of chapter 7. Oh, centripetal forces as well. I think that this time we'll go on and continue with the problems, but next time we'll sort of have a help session. So like in between now and then, y'all have some time to look at some of these problems, and then we can address those. But we're dealing with chapter 7, which is kinematics, centripetal forces, that is that the sum of the forces equals mv squared over r. We worked a couple problems in class like that, and you have some in your homework as well. And then in chapter 8, check at all the topics here. We had torques. Gonna have to do a cross product to make sure you're up on that. We had moments of inertia. I is sum of mr squared. You'll also need to know how to use that table of values for moments of inertia that I showed you in class, and that we derived some of those. Remember, the derivation will be 10 points from your exam, so please make sure that you come in with that derivation ready to turn in. Let's see, Newton's second law related to this, that is that the sum of the torques equals I times alpha. We had a couple problems like that. So like for example, one where you have some torque acting on an object and need to find out how it's accelerating. There might also be some simple kinematics questions wrapped up in that. So if an object is accelerating, how far does it accelerate in a certain amount of time? What is its angular velocity in a certain amount of time? That sort of thing. We worked a couple examples in class, a couple examples in your homework as well. Let's see, rotational kinetic energy. That is that kinetic energy is 1/2 I omega squared. And then also don't forget the work energy theorem. Work is equal to change in energy. So for example, if I ask how much work is required to stop a rotating object, then you can just calculate what is the energy, because the work required to stop a rotating object is equal to the amount of energy that it has. That's the work energy theorem. Derivations are on the take home. And then I guess it's just conservation of momentum. That is that Li equals Lf. Right, a couple of different things you could see. Like we worked a problem in class where we had the merry-go-round and the kid jumps onto the merry-go-round, something along those lines. Or also we worked a problem where we had like a flywheel, for example, on a shaft, and then we added a bar to it, like that, where it changes the moment of inertia, and you have to find out what is the new rotational speed, the new angular speed, right? Something along those lines. So certainly you'll see a cross product. Certainly you'll see this, which wraps up with moments of inertia. You may or may not see the kinetic energy. You likely will in some way, but and then also this conservation of momentum. Right, and that's all of chapter 8. It'll probably still be a normal length test, right? So, 15 or so multiple choice, 4 to 6 free response. It's just they'll be worth fewer points because there'll be fewer points on the test. There'll only be 90 points on the test. Okay? Are good with that? Oh no, less than that. I'm sorry. 60 points on the test, right? Because 30 are take home, 10 are take home, and then the rest is in class. 10 is the derivation, 30 for the thing that'll be due after the break. Okay? We'll have some time on Wednesday because the test isn't until Friday. We'll have time on Wednesday to go over things in more detail. So between now and then, please take a look at the homework, sort of find out where you're weakest, and then on Wednesday, about half the class or so, we'll devote to spending on that material. You good with that? Yeah. I want y'all to do well on this test. Some of you need a good grade on this test, okay? Going into the final. Everybody needs a good grade going into the final so that you're just being on good footing. All right, let's work through a couple of these problems. Everybody got the handout, the problems I gave you? Yeah. Your test questions will be similar to this, but they'll be take home, and you'll be allowed to use outside resources and what have you. Let's see, I don't think I have these, so I'm just going to sort of do my best to sketch them. The first question is about this gymnast. And by the way, on all of these questions, we're going to be using stuff that we've been doing so far. That is, like in chapter 4, when we said that the sum of the forces is equal to 0, and then again in chapter 8, where we say that the sum of the torques is equal to 0. In all these cases, these are static problems. That means that the acceleration of the system is equal to 0, and the angular acceleration is equal to 0. So very similar to problems that we've worked so far. The only difference between these and the ones we did in chapter 4 is really the number of unknowns. We have more unknowns, but since we're now dealing with torques, we can use that idea that the torques, the sum of the torques are equal to 0. we can use that idea to add another system of equations, which will allow us to solve for more unknowns. So this first one is pretty simple. We're going to work two variations of this. First, the cheerleader or the gymnast, as she's drawn on your figure, and then there's a second part to the question where she bends her front knee and it changes her moment arm, the length of her moment arm. Let me see if I can sketch out this cheerleader. There's her head, there's her body. That's about it, right? Okay, so I have some distances here. First, I know that her weight is equal to 700 newtons. All right, I know that the distance from her feet to feet is 1.8 meters, and that her center of gravity sits 0.3 meters above the line of her legs. So this is her center of gravity. That's our center of mass. We discussed that in lab. That's the point where all of our mass can be considered to be located. And for most people, your center of mass is sort of right inside your belly, as they show it here. All right, so my center of gravity, our center of mass, is 0.3 meters above the axis along her legs, and then her legs are split evenly into 0.9 meters and 0.9 meters. All right, and the first question is pretty simple. I just want to know the force exerted on each foot by the floor. And there are two systems of equations that I can write. I can write that the sum of the forces equals 0, and then I want to label all the forces. So what are the forces that I have acting here on the gymnast? Okay, I have the gravitational force. It acts at the center of gravity. So I have the force weight. That's equal to 700 newtons. What are the other forces that I have acting? I have normal force. Where is the normal force located? Whereabouts? It's at both of her feet, in fact, right? So in this, maybe I should show y'all. But if I could do a split, like it's her feet that are supporting her. So
She's doing a split on the ground.
she's doing a split on the ground,
Okay.
right? Oh, do you think she's up in the air?
In the air, so normal.
No, I'm sorry.
I got you.
Yeah, she's doing a split on the ground, and so her feet are supporting her, and so I have normal forces here and here. Now we know because of the symmetry of this that the normal forces are going to be related how? Is the one on the left going to be more, less, or the same as the one on the right? Same. All right, but we can go through the process and we'll show that that's true because in the next part of this problem, that won't be the case. I'll show you how that changes in just a second. So I have the sum of the forces equals 0. I'm going to call these Fn1 and Fn2 for now, just to keep them different, not assuming yet that they're the same. So I say Fn1 plus Fn2 minus Fw equals 0. All right, Fn1 plus Fn2 minus Fw equals 0. So this is equation number 1. All right, as of now, I have two unknowns in this equation because I don't know Fn1 or Fn2, and I'm not assuming right now that they're the same. All right. And then the second equation that I can write is the sum of the torques equals 0. Now in this is sort of the tricky part in these, is determining what is your axis of rotation. And when you have an object that's in a static situation, you can use any axis of rotation that you want. So because she's not really rotating, right? I can say that my axis of rotation is here. I can put it here. I can put it here. I can even put it here at just some random spot. So I want to choose my axis of rotation, and that's sort of the trick in these problems, is choosing the appropriate axis of rotation so that you get rid of a variable that you don't know, and you only include variables that you do know. Because if you have your axis of rotation at the point where the moment arm is 0, then that force doesn't provide any torque. So where might we put our axis of rotation on this gymnast? Okay, we can put it at Fn1, right? So then when I add up the torque, if I put my axis of rotation here, Fn1 is going to provide no torques at all. You follow me on this? Right, so it's a trick, but it's a useful thing because it gets rid of one of those unknowns. I could also put my axis of rotation somewhere else. Where might that be? Whereabouts? At where? On our other foot, right. I could also put my axis of rotation here at Fn2. It doesn't really matter where you put it. It still gets rid of one of those unknowns. So I'm going to put my axis of rotation right here. And then I can do the sum of the torques. By the way, you could put your axis of rotation in the middle at the weight, or you could really put it anywhere, because then you'll still have a system of two equations with two unknowns, but you can make solving those equations simpler by getting rid of one of those unknowns in the second equation. You'll follow what I'm saying? If I put my axis of rotation at our center of gravity, right here, then I would have an equation that would have both Fn1 and Fn2, but I would still have this one, and I could solve the two and find both of those unknowns. But let's set our axis of rotation at Fn1, and then I will just sum up the torques. I'm going to call this torque W, and I'll call this torque N2. Torque W, is it positive or negative? That is, does it cause clockwise or counterclockwise torques? Torque W, due to the weight. Right, it causes clockwise, so the sum of the torques will be negative torque W. And then Fn2 causes a counterclockwise, so that's going to be plus torque N2, and then that's equal to 0. Now I can further go with this, and my torque due to the weight is going to be negative times her weight, which is 700 newtons, times 0.9 meters. Plus torque N2, which is going to be Fn2 times 1.8 meters. And then this is all going to be equal to 0. So now you're going to solve for Fn2. What you got there? Which we shouldn't be surprised, right? That's half her weight. And so that's sort of what we thought going in. But just going through that process, I find that Fn2 equals 350 newtons. And then I can take that and put it in up here, and I get Fn1 plus 350 minus 700, which is my weight, equals 0. And then I can also solve for Fn1, which is 350 newtons. All right, so that one's pretty simple, right? And you could have a very simple statics problem like that on your take-home part, but you'll have some that are more complicated as well. Now, this problem is made more difficult. Let's say that instead of doing a split like that, let's say that our front knee is bent. All right, so y'all seen people do splits? Like you can do splits like this, or you can bend that front knee, right? You get the idea? Like your knee is supporting you instead of your foot. So this figure would look a little bit different. I'm going to erase all the calculations. Is that okay? All right, they're going away. And it becomes less obvious what the normal forces should be if we have a situation there's our foot, but actually we're not having that anymore. Now her knee is bent like this. So there's our foot right there. And now instead of having Fn1 acting at our foot, Fn1 is now acting on our knee. Okay? Y'all follow what I'm saying? Alright, so that means that my, if we assume that her knee bisects her leg, which is a pretty good assumption, that means that this distance is what? 0.45, yeah, so I bisect that 0.9 meters. So I have 0.45 meters there and 0.9 meters there. Alright, so now we can go through a similar thing where we find the normal force at 0.1 and the normal force at 0.2. Similar deal, where we say the sum of the forces equals 0. That's going to be Fn1 plus Fn2 plus the weight, minus the weight, equals to 0. All right, but in this case, we know that Fn1 and Fn2 are definitely not going to be the same like they were in the previous, because the system is no longer symmetrical. She has one moment arm that's very short and one that's longer. The legs. You have a question? No? All right. Now, what does the second equation look like? If I write the sum of the torques equals to 0, what does that look like? What would you use as your pivot point in this case? Okay, we could use Fn2. Let's try that. So we're going to take this as our pivot point. Remember, you choose whatever pivot point you want. It doesn't really matter because the system isn't rotating anyway. It's sort of just an imaginary pivot point. So if I choose that as my pivot point, write out what are the sum of the torques. You're going to have torques due to Fn1 and a torque due to Fw. So you want to ask yourself, is Fn1 positive or negative? Is Fw positive or negative torque? And then go from there. Torque N1, positive or negative?
Well,
It's clockwise or counterclockwise? No. If I imagine that I'm rotating about this axis, this force causes rotation in this direction, and this force causes rotation in this direction. So this force causes a clockwise or counterclockwise? Clockwise, right? So that one's going to be a negative, and then my Fw causes a positive torque. So I have negative torque N1 plus torque due to the weight. Really, though, if you get that messed up, it's not terribly important because this is a static situation. All you know really is that the torques are equal and opposite. So it's not terribly important that you get the signs correct on this like it was in our dynamic problems. All right, so torque N1, this is going to be negative times Fn1 times, what's the distance? Actually, remember, this is my axis of rotation. So it's the distance from here all the way over to here. Yeah, it's going to be 1.35 meters. Plus weight, which is 700 newtons, times 0.9. And that's equal to 0. And then from that, we can calculate what Fn1 is. Somebody have Fn1? Okay, yeah, that's what I got as well. I'm just going to call it 470 newtons. All Alright, so notice before, gosh, our normal force was 350 on each. So now we have a much larger normal force on our knee than we had on our foot in the previous part. So that means that our normal force on our other foot will be less than 350. Right? So I can take that Fn1 and we can go back up here, because I still know that the sum of the forces has to equal 0, and I can put in that I have 470 newtons plus Fn2. I feel like I'm cursing every time I say that. Fn2. But minus 700 equals to 0. And then we can solve that for Fn2, which is 700 minus 470, or 230 newtons. Alright, so these aren't really much different than what we've done before. The only difference here is that we're adding in this separate set of equations. The approaches that you take to them are sometimes different, though. So those of you going into engineering, you have a whole class that's just based on this. Let's look at the next problem. And this will probably be our last one. But it has a couple parts. I have a bridge. There are a couple scenarios. You have this bridge, and it's supported entirely by the hinges and the shore. So the cables in this case are completely flat. And it just wants to know what fraction of the weight is supported by the opposite shore if the point of support is directly beneath the cable attachments, and what is the direction and magnitude of the force the hinges exert on the bridge under these circumstances. It says the mass of the bridge is 2,500 kilograms. Let's see. Alright, so I have this bridge. Right now we're not worried about the cables at all. So you have this figure. I don't think it came out real great in the copy, but you can sort of see. And then the bridge comes here. It has a hinge right here. The center of mass is right here, so I can imagine that all the weight is at that point. And then this distance, it says, is 1.5 meters. And this distance then, the total length is 9 meters, so this distance is 7.5 meters. And then this side of the bridge is supported by just the ground. Huh?
That would be the ground.
Yeah, this is the ground, so that's the right side of the bridge. It's just supported on the bank of the river or whatever, the moat. Okay, and let's see, I'm asking for here, what is the normal force? Yeah, what is the normal force? And also in this case, it does actually talk about the angles. What is the direction of my hinges? In this case, our forces are all going to be either up or down. So I'm going to work through this part. I have a force that's due to the hinges in this direction. See, I call this, we'll just call this F, or yeah, F. And then we have a force over here, which is our normal force. So we have three forces acting here at different moment arms. And I can say two things. I can say the sum of the forces equals to 0. And you can say the sum of the torques equals to 0. And I am trying to get to, what's it asking for? Yeah, what fraction of the weight is supported by the opposite shore? So I want to know, what is this normal force equal to? All right, I'm going to give you a few minutes to get a head start, and then I'll start helping you with it. So right now I just want to know, what is the normal force? You can write out your equations for the sum of the forces. There are only 3 forces involved. Then you choose a rotation point, an axis of rotation, and you can write out the sum of the torques equals to 0. write out the equation for the sum of the torques. And then from those, you should be able to solve for the normal force, and then you just take the fraction of that, the normal force over the weight. The weight is given 25,000 newtons. 2,500 kilograms, so 25,000 newtons. Yeah. Some of the forces include F plus Fn minus Fw equals to 0. Why is it that I've drawn the force due to the hinges straight up? How is it that we know that? That might not be obvious from the beginning. What about the forces tells us that the force F only has a y component and no x component? That's right, because there's nothing pushing in the x direction. So, for example, if this force, the normal force, we know the normal force is perpendicular to the surface, so the normal force has to be straight up, and the weight has to be straight down towards the surface of the Earth. And since there are no other forces that are pushing in this direction, then there are no x components to this force. Right? If there were forces, like if this normal force was in this direction, as we'll see in just a second with the tension in the navel, then this force would have to be at an angle. But because there are no other forces in the x direction, we know that this force has to only be in the y direction. That probably makes intuitive sense to you as well, but that's the reason, is because there are no other x component forces. Well, that's for the next problem. Yeah. So right now we're saying that the tension in the cables is completely zero. It says that it's slack. All right, so and some of the torques, what did y'all choose for your axis of rotation? The hinge? Okay. We can take that as the axis of rotation. So I'll take that as my axis of rotation. And then I can say Fn times 9 meters minus Fw times 1.5 meters. That's right, Josh? Yeah. That's equal to 0. All right. I know that Fw is equal to 25,000. So I can solve this for Fn. And Fn is 4,200. That's what I got. Where is it? Yeah, 4,200. All right. So that's my normal force, and then the problem was asking what? Oh, we're looking now, what fraction of the weight is supported by the opposite shore? So now we want to know what is the fraction. The problem is actually asking what is Fn divided by Fw, which is 4,200 over 25,000, which is, I think, about 0.6. No point, is that right? 4,000. 0.16, is that right? Okay, yeah, so we'll just say 0.2. All right, So here, Josh chose this as an axis of rotation, which was a nice thing because we're looking for the normal force, and when we do this, then we can find the normal force pretty simply. Like we don't need to use this at all, right? This set of equations. I don't think we have time to do the next one. The next part of this we'll actually consider the cables. We'll do that one next time, and that'll be a good preparation for sort of the take-home portion of the test. Again, the take-home portion, the concepts aren't that complicated. It's really just sort of the approach to solving the problem, choosing your axis of rotation, and applying the equation appropriately. You usually get a system of equations that you have to solve, and we'll do one like that next time, where we have angles involved. We'll also take some time to answer questions about the test coming up on Friday. So if y'all make sure you look at the homework and sort of see where you're lacking, and we can address those questions on Wednesday. Any questions about that? What to expect? Just sort of winding down. We will have a general education assessment. It's a multiple choice, like a 20 or 30 question little test. It's going to count towards extra credits. It won't be only a couple points or so, but you know, if you're on the borderline, it'll be good to have a couple points. That'll be on Monday after we return from the break. All right. Otherwise, on that Monday, I'll sort of go over what to expect for the final exam, which will be a few days after that. All right, almost done, folks. Keep it up this week. I know you have a rough week. All right, tough week. Yeah. I'm sorry.
And also, I think we do a speech Friday. And then all my classes are back to back.
Oh, well, I'm sorry. Sucks to be here. It's okay. Have a good day. It'll be okay. Just take a deep breath. Get plenty of rest.